You may have heard of the cell membrane and how it functions to be an impenetrable wall, stopping larger and charged molecules from moving through it. What if I told you, though, that there were a couple of ways for those molecules to sneak through? Let's talk about one of the more interesting ways, the voltage-gated ion channels. Voltage-gated ion channels are cell membrane channels that are sensitive to the voltage around them. This voltage is a result of the net charges of all the nearby ions. Let's first watch the process entirely, and then we'll break it down. Alright, now it's time for the breakdown. The key to understanding voltage-gated ion channels are that they have 2 gates and 3 states. Let's first talk about the 2 gates, the voltage-sensitive gate and the inactivation gate. The voltage-sensitive gate will open or close based on the environmental charge distribution. The threshold is the membrane potential at which the gate undergoes conformational change. The inactivation gate, on the other hand, is special. It doesn't rely on charge. Instead, it closes, blocking the channel at a set time period after the other gate is open. This time lag is known to be 0.5 milliseconds. The gate and its mechanisms are best described by the ball and chain model. As these gates move around, the channel will cycle between 3 states: active, inactive, and closed. We will go into more detail on when each stage occurs, but first, let's talk about how and why the gates will move. It's important to remember that the channels, along with their gates, are made up of amino acids, some of which can be charged. And so it makes sense why, then, when the charges change across the membrane, we would see the voltage-sensitive gate undergo a conformational change and move, being attracted towards an opposite charge. For the sake of simplification, we'll observe how a voltage-gated sodium channel works. For these channels, the default state is closed. The voltage-sensitive channel is closed while the inactivation gate is open, and there is no net movement of sodium ions through the channel. As the concentration of sodium ions around the channel increases, we see a rise in membrane potential. Once a threshold is reached, which for sodium channels is negative 55 millivolts, the voltage-sensitive gate opens, leading to sodium ions flooding into the cell. In the open state, the voltage-sensitive gate and the inactivation gate are both open. Alright, now we're on the final state, the inactive state. In the inactive state, the voltage-sensitive gate is open while the inactivation gate is closed. As mentioned earlier, the inactivation gate closes at 0.5 milliseconds after the voltage-sensitive gate opens. This is because the opening of the voltage-sensitive gate favors the closed conformation of the inactivation gate. The reason for the time lag is that it just takes longer for the inactivation gate to close. Alright, now for the quick review. We see ions move around in a random manner, and once enough sodium ions gather near the voltage-sensitive gate, the threshold is reached and the gate opens. 0.5 milliseconds later, the inactivation gate closes, and finally the membrane potential eventually drops below the threshold and everything is reset.